Everyone, welcome to ABT Tutoring, where learning is as easy as ABT. Now, welcome again, guys. Now, today we're going to do Introduction to Sets, or part 1 video on sets. Now, the first thing I'm going to ask you guys, what is a set? Now, a set is simply a collection of items or elements, generally called elements. And elements is something that we're going to discuss further on in this lesson, right? Now, a set can either be well-defined or guess what? Not so well-defined, right? Now, that seems self-explanatory, right? All right, but let's still go through it anyway. Now, a well-defined set is a set that can be counted. You can count the number of elements in the set, right? So, for example, let's look at a set. Let's say set A, where we have multiples of 3 less than or equal to 18. So if we write our set A would be equal to 3, 6, 9, 12, 15, 18, right? Pretty straightforward, well-defined. Now, a not so well-defined set or a non-well-defined set, I'm going to get a little crazy here, but think about this. Let's say counting the sand grains. Now, what does that look like? How can you do that? Crazy, right? Impossible. So we're not going to do that. Now, let's touch on elements. Now, as I stated earlier, an element is an item in a set, right? For example, if set B is the numbers, the whole numbers less than 6, so set B is equal to 0, 1, 2, 3, 4, 5, then an element in set B would be 0, another element would be 1, another element will be 6. I mean, by now you get the point, right? All right, so that would be the elements. Now, if we wanted to know the number of elements in set B, we'd simply count them, right? So it'd be 0, 1, 2, 3, 4, 5. So what do we have? 6 elements in set B. Now I want to jump into 6 areas that we consistently see in sets. Finite versus infinite sets, null or empty sets, universal sets, subsets, equal sets, and equivalent sets. Now, finite versus infinite sets. So now this is English language, right? What is infinite? Now, infinite means endless, limitless, right? So if we were to bring that back to terms in terms of set, that would mean, let's define a set B now, and B is equal to whole numbers, right? Now, what that would mean is that we'd count B 0, 1, 2, 3, and I'll never stop, right? It's endless. So infinite sets, straightforward. Now, if we jump to finite sets, quite the opposite, right? It means that it has an ending, there's a limit. So we could say whole numbers less than 10. Now, that's a totally different story. That's 0, 1, 2, 3, all the way to 9. We'll cut off at 9, so it has an ending. And that's pretty much the difference between finite and infinite sets. Now, next point, null or empty set. Now, what is a null or empty set? This is a set that has no elements. 0 elements, no elements, right? So that is a null or empty set. Now, a general misconception is where you show a set that has 0, the number 0 in there, the whole number 0. Now, that is not an empty set. The element, there's an element in there, 0. Common misconception, that is wrong if you call it an empty set or a null set. Thirdly, let's discuss universal sets. Now, we're going to start off with the English again, right? I'm going to bore you with the English again. What does universal mean? Now, universal pretty much means inclusive, considering all, factoring in all cases. Now, if we apply that same thinking or logic to mathematics, the universal set would include all or consider all cases or, get this, take in all elements of the set or of what we're looking for, right? And that is pretty much universal sets. Now, if it's a little murky, if we don't understand it so clear, don't worry. We're going to touch on it a little more and hopefully down the line we'll be able to clear it up some more. Now, the next concept I'm going to talk about is subsets. Yes, I know. Where is he going with this again? Back to the English, right? Now, what do we mean by sub? What's the English meaning of sub? It means lower, lesser position, right? Now, Asafa calls himself the sub 10 king. What does that mean? He's running less than 10. So if we were to analyze that, then we could say, but I'm going to jump to an easier example, right? If we look at whole numbers less than 6, let's define a set F with whole numbers less than 6, right? So we have 0, 1, 2, 3, 4, 5. Whole numbers less than 6, right? Now a subset of that would be if we were to break out a set, let's say G of 0 and 1, or H, 1 and 5, or let's say I, 3 and 4. You guys get the point, right? Those would all be subsets of or previously defined set F. Now another way of saying subsets is we can say that G is contained in F, or H is contained in F, or I is contained in F. Those would all mean that they're all subsets, that G, H, I are all subsets of F. Now the next one that we're going to move to is equal sets. Pretty straightforward. It just means that they're equal to, the sets are equal to each other. What does that mean? Simply, as I spoke about contained, it would mean that, let's say we define two sets, they're both contained in each other. That's what an equal set would be. So if we define two sets, let's say J and K, I'm running out of alphabets here, bear with me. J will be contained in K, and K will be contained in J, and those would be equal sets. Got it? The next one that I'll jump to quickly is equivalent sets. What does that mean? It's simple. When we look at the number of elements in each set, let's say we use set X and set Y, the number of elements in set X is equal to the number of elements in set Y, and that would give us our equivalent sets. And that was 6 simple areas that we'll normally see in sets. Now I'm going to jump to something simple again, Venn diagrams. Now I know you guys and girls are saying that I use the word simple a lot, but trust me, it's simple, right? Now what is a Venn diagram? Now a Venn diagram is simply a rectangle, right? And what we do, we have in that the universal set. Remember that word? Universal set is in the Venn diagram. And what we do now, we add 2 circles in the Venn diagram that may be disjoint or joint, and you'll hear more about that later, don't worry. And that pretty much accounts for everything that we need to do for a Venn diagram. Now there are a few concepts that we definitely need to go through before we dig deeper into the Venn diagram. And don't worry, by the end of this video, you'll understand them all. So the first one that I'll touch on is set complements, there's set intersection, there's disjoint sets, and there's set unions, right? 4 simple concepts, addition to what we did before, that we need to go through. I'll start with set complement. Now, I know by this point everybody's wondering, is he doing English or is he doing math? Because he keeps saying, what about English, right? So let's start with compliments, right? And I'm not talking when you talk to the girl or the boy that you like and you say, hey, you have really nice eyes. Not that compliment. This is another compliment. This means pretty much in addition to, right? That's a compliment. So that's the English, right? Now again, let's bring it back to the math, right? With set complements, let's say you define a set, let's say A, right? Now if you define a set A, your set complement of A would be everything that is not in A, all right? Example, you have a universal set, right? Let's say whole numbers less than or equal to 8. So that's A equals 0, 1, 2, all the way to 8, right? Now, let's say you have a set B, which is a subset of the universal set, right? That is odd numbers, right? So we're talking about 1, 3, 5, 7. Now, what would be the complement of set B given the universe? Now, the complement of set B would be everything that is not in B. So what does that mean? 0, 2, 4, 6, 8. Simple as that, right? Now the union of set A, of set B and B complement gives us the universe. Next one I love to jump to is set intersection. Now what does that mean? When we talk about intersection, again with the English, right? It means where 2 areas intersect. All right, let's not use the same word to define. Where you have an overlap, where they meet. Perfect. Now, let's think about 2 sets again. Let's say X and Y. So let's say that set X is positive integers less than 10. So we go 1, 2, 3, all the way to 10. And set Y is prime numbers less than 17. So help me out with this one, guys. What's that? 2, 3, 5, 7, 9. No, not 9. Just checking if you're listening. 11, 13, right? So those would be X or positive integers up to 10, and Y, our prime numbers less than 17. Now, what in those 2 actually intersect? What is common in both of them? What do when we look in set X and we look in set Y, we see both, right? We see 2, 3, 5, and 7. And the intersection of X and Y, or X intersect Y, would be equal to 2, 3, 5, 7. Now, if we have 2 sets, right, and the intersection, let's say we have a set V and a set W, let's say set V equal even numbers, set W equals odd numbers, right? Now, if we have a set V and a set U, and when we look at the intersection, it's an empty set, which would be what happens there, then we would say, you know, that's a disjoint set, which means they're not connected. So when you have an intersection of two sets, right, that give you an empty set, that's what we call a disjoint set. So there you go. I just explained disjoint sets easily, right? It flows perfectly from intersection. Now, set unions, right? All right. So let's think about a marriage. All right, I know, I'm corny, but bear with me. Now, similar to a marriage, right? Unions you combine, right? So let's look at, let's say a set F, assets of a female, and a set M, assets of a male, and we're going to do the union. We're going to combine, right? Now, with a union, you combine the assets here of the female, the assets here of the male, you bring it together, and what intersects, let's say what they brought together, right, we remove, right? And that is pretty much the concept of a union. Now, suppose we want to know what is the number of elements or number of assets for a F union M. That would simply be the number of assets for F plus the number of assets for M minus the intersection, or what they brought together, of F and M. So that would be N of F plus N of M minus N F intersect M. Another way to look at a set union would be, let's say, same example, the union of F and M, right, or F union M would be the number of assets in F only plus the number of assets in M only. How do we get the number of assets in F only or the number of assets in M only? The number of assets in F only is equal to the number of assets in F minus the number of assets in F intersect M. And the number of assets in M only is the number of assets in M minus the number of assets in F intersect M. Now let's do an example. In a class of 35 students, 29 play draughts, 16 play chess, 10 play both. Each student plays either draughts or chess. Now, find the number of students for draughts only, and 2, find the number of students for chess only. So now, following that example, the number in our union is 35. The number for draughts is 29. The number for chess, 16. And the number that do both, the intersection, right, is 10. Now, remember how to find the number who do draughts only and chess only. I just told you. So for draughts only, so that would be equal to the number for draughts minus the intersection, right? So that's simply 29 minus 10. Easily. What's that again, guys? 19? I would say yes. As simple as that. Now let's do chess only. So that's chess only. Again, simply the number of chess minus the intersection, right? What's that? 16 minus 10. And what we get there? 6. As easy as Sunday morning. Now let's look at another question. In a group of 60 students, 31 speak French, 23 speak Spanish, and 14 neither French nor Spanish. Determine the number of students who speak both French and Spanish, French only, Spanish only. Now, a simple breakout for this question. The number of elements in the universe is 60. The number of students in French is 31. The number of students in Spanish, 23. The The number of students that do neither French nor Spanish is 14. And let's say, French and Spanish, we denote that as X for now. Now, when we look at our Venn diagram, we have our universal set defined. The students who do not do French or Spanish, 14, and then the rest. So French only would be our 31 minus the intersection. Our intersection we define as X, which is French and Spanish. And Spanish only is our 23 minus X, right? Or Spanish only. Now, if we want to find X, what we can simply do is add all elements to equal the union, because as we know, everything in the rectangle is a part of the universe. So let's do that. So we can say 31 minus X plus 23 minus X plus 14 is equal to 60. Now, minus X plus X cancels. 31 plus 23 is 54. 54 plus 14, 68. So we have 68 minus X is equal to 60. Now, we can carry over X that side and carry over the 60 the next side. And we end up with X being equal to 68 minus 60, which gives us 8. What does that mean? The number of students in French and Spanish is 8. Fortunately for us, that was the hardest part of the question. Now it's to find French only and Spanish only, which we know how to do, right? So we would have found the intersection. We have it here perfectly. So the number for French only is equal to the number in French minus the intersection. And for Spanish only, the number in Spanish minus the intersection. This is equal to our 31 minus X. This is equal to our 23 minus X. We know what X is. So this is our 31 minus 8. And this is our 23 minus 8. Right? And there you have it. Can anybody tell me what this is? Your guess is as good as mine, 23. Can you tell me what this is? Oh, I wrote X. 15. All right, and that's it. As easy as that. So, French only, 23. Spanish only, 15. All right, thanks guys. Thanks for joining ABT Tutoring today. I hope this session was really helpful. I enjoyed it. I hope you enjoyed it as much as I did. This was really fun. I hope to see you on sets part 2, which will be coming shortly. It's in the video link. Please go through this video, go through the next one. It's lovely stuff. I really enjoyed it. I hope you did too. Have a good one.